In this section of the course, we'll learn about variables and constants. It's virtually impossible to write a C++ program without using variables. Variables are a fundamental concept in programming languages. First, we'll learn what variables are and how to declare them so we can use them. There are rules for how we name our variables, and there are also style issues to discuss as we go along. Then we'll go over some of the primitive types in C++, such as integers, floating point numbers, booleans, and characters. We'll also learn how to determine how much storage is allocated to variables by using the size of operator. Then we'll learn about constants, what they are and what they're used, and why they're so important to keeping our code correct and modifiable. We'll learn how to declare and use constants, understand literals, and constant expressions. This section is very straightforward and easy to understand. However, the concepts you'll learn in this section serve as fundamental building blocks in C++ programming, since nearly every program you write will have variables and constants. Let's get started. In this video, we'll learn what variables are from a conceptual perspective. This will allow you to better understand how to use variables in your programs. I'm assuming in this course that everyone is familiar with the basic architecture of a typical computer system. That is, memory, a CPU, and a bus that allows the movement of data between the CPU and memory. Random access memory, or RAM, is a contiguous block of storage used by the computer to store information. This information can include computer instructions as well as data. RAM can be thought of as having memory cells, where each cell has an associated location. If we had to program using the specific memory locations, it wouldn't be a lot of fun, and we'd likely have a lot of programmer errors. Imagine saying something like, move 21 to memory location 1002. In many very low-level languages, this is sometimes what we do. However, most programming languages allow you to associate a name with a memory location. Let's see the same example using a variable. In this example, you can see that the memory location 1002 has been associated with the name age. In computing, this is called a binding, and we can move 21 to age. This allows us not to have to worry about what exact memory location age is associated with. If we run the program again, age will likely be associated with a different memory address, and that's okay, since we never knew about it in the first place. Our code will still work. Also, thinking of names that make sense to us makes writing and reading programs much easier. That's the basic idea behind names and variables. Of course, since age is a variable, that means that its contents can vary. So if we turn 22 years old, we can change the value of age from 21 to 22. So to recap, a variable is an abstraction for a memory location. We use abstractions all the time in programming to make it easier for us to deal with complexity. Variables allow us to use a meaningful name to represent a value. It's important to understand that variables have two main properties. First is their type. The compiler needs to know what types of values are legal to store in age. In the first code snippet on the left, we tell the compiler to store 21 in age, but we never told the compiler what is valid to store in age. This will produce a compiler error telling us that age hasn't been declared. In the code snippet on the right, we first declare age to be an integer. Now the compiler knows that only integers are allowed to be stored in age. This is called static typing because the compiler is enforcing these rules when the program is compiled rather than when the program is executing. So remember, variables must be declared before you use them in C++. Their value or contents may change as the program executes. In the next video, we'll learn how to declare and initialize variables so they're ready to use in our programs. Let's go there next. In this video, we'll learn how to declare and initialize variables. Then we'll head over to CodeLight and declare and initialize some variables in live code. The syntax for a variable declaration in C++ is very simple. First, you tell the compiler what the type of the variable is. Then you tell the compiler what the name of the variable is. And finally, you terminate the declaration with a semicolon. Later in this section, I'll go over some of the basic C++ types, but here are a few as a preview. Int is an integer or a whole number. A double is a floating point number. And a string is a sequence of characters like you would see in my name Frank. Also notice that we can declare variables of non-C++ built-in types. One of the very powerful features of C++ is object-oriented programming, which allows us to create our own types. So we can create variables that represent an account or a person using the same syntax as we used for integers and doubles. This is great since it makes our program so much more readable. In the next slide, we'll talk about some of the rules that you must follow when you name variables. Remember, in C++, we must declare our variables before we use them. So let's take a look at some of the variable naming rules. The rules for naming C++ variables are very, very simple. C++ variable names can contain letters, numbers, and underscores. However, the first letter of the name cannot be a number. It can be an underscore or a letter. As discussed previously, C++ keywords are also reserve words, so you can't use those names. You can't use int, you can't use double as your own names. Also, you cannot declare a variable name that's already been declared in the same scope. So if you declared x to be an integer, you can't do that again. Remember, C++ is case sensitive, so the name age in uppercase is considered different from the name age in lowercase. Let's take a look at a few examples. In the left column of the table, you can see some legal C++ variable names. Since C++ is case sensitive, age beginning with an uppercase A is considered a different name from age beginning with a lowercase a. We can begin our variable names with underscores or letters, and we can also have underscores and numbers within the variable name. The right column has some examples of illegal variable names. The first example is lowercase int. This is not allowed since lowercase int is a reserved word in C++. We cannot have special characters like the $sign or mathematical characters like the plus sign. Also notice that variable names cannot have spaces in them. Now let's talk about cout. Cout is a little different. Cout is a legal name because it conforms to the variable naming rules. However, if you include IOStream in your program, then cout is already defined somewhere else. It's defined by the standard library, so it no longer becomes a valid name. Since it's been defined somewhere, you cannot redeclare it yourself. So the rules that the C++ compiler enforces for variable names are pretty simple, as you can see. Now let's take a look at variable naming style and best practices. The most important thing you can do is to be consistent with whatever naming convention you choose to use. There are many style guides and naming conventions out there. In many cases, you'll be working for a company and they have a specific style and naming convention that you have to use. This has nothing to do with the C++ compiler, but it's still very important. For example, Google has a published C++ style guide, as do many other companies. One of the first decisions you make with regard to variable naming is whether you want to use camel case or underscores to separate words. Both styles make the text more readable by avoiding long streams of lowercase letters, which are harder to read. Camel case capitalizes the first letter of every word in your name and doesn't use underscores. The other style is to use underscores to separate words. Either style is fine. The important thing is to be consistent. In this course, I'll use the underscore style. Please use meaningful names. Don't use obscure abbreviations. For example, instead of using the variable name MOE to represent the mass of the Earth, just use the real name, mass of Earth, with underscores or camel case, either way. Sure, it's a little bit more typing, but your program becomes so much more readable and maintainable. Never use variable names before initializing them. Uninitialized variables can cause all kinds of unexpected results in C++. I'll show you an example of this when we head over to the IDE. Finally, it's best practice to declare your variables as close to when you need them as possible. In other words, if your program uses 10 variables, don't declare all 10 of them at the top of the file and then use them later. Instead, declare them right before you use them. There are many, many more programming best practices, and we'll discuss them throughout the course. So now let's talk about initializing variables. Notice the first line of code in this example, int age. This is a variable declaration that's uninitialized. You have no idea what the value of age is. And that's the problem. If you try to display age, or perhaps use it in some calculation, you'll run into problems because it was never initialized, so its value could be anything. Uninitialized variables are a very common source of programming errors. C++ provides 3 ways to initialize variables. All 3 are equivalent and they're related to the way that C++ has evolved over the years. The first is to use an assignment operator. That's the equal sign. This will assign 21 to age right when it's created, so it will be immediately initialized. The second uses parentheses around the value, in this case 21. This is a constructor-style initialization. We'll talk about constructors when we talk about object-oriented programming. The final initialization statement is the C++ 11 initialization syntax. This style of initialization is consistent across different types in C++ and has some benefits that we'll discuss later in this course. I encourage you to use this style of initialization. Now, let's head over to CodeLight and see some of these examples in live code. Okay, so now I'm in CodeLight, and let's write a real simple program that calculates the area of a room in square feet. So the idea is we'll ask the user for the length of the room and the width of the room, and then we'll multiply those two together to calculate the square footage of the room, the area of the room. Okay, now obviously we need two variables, but before we do that, let me show you one of the issues with uninitialized variables as we talked about in the previous slides. Let's create a real simple variable here called age, just like we did before, and I'm not going to initialize it on purpose, and what I want to do is just output that value to cout. Let's build this. And I'll execute it, and you can see what's printing out here. You can see there's age, I'm outputting age, and that's the value that's in age right now. Not what we expected, for sure. The problem is that we never initialized the variable age, so the value that's in that variable could be anything, and in this case, it is anything. Okay, so let me show you how that works. So let's go back to our conceptual model. Here's our memory. I've got a memory location. Let's say that that's memory location 2000. That could be anything. And age is associated with that location. Now, in there are a series of zeros and ones. That's how we store values in computers. Whatever value happens to be in there is the value that will be displayed on the console. Remember, when I output age, the compiler is going to grab whatever this value is in here and replace it right in there. In this case, we got that really strange, very large number. The idea is we really want to initialize this guy to something, even 0, before we use it. So you can see here, I'm using it before I initialize it. That's not a good idea. Okay, so let me clear this. And if we now initialize this to, let's say, 0 or 21 or whatever we like, I'll use 21 here. Now we'll build and run. You can see now it's printing out 21. Okay, so that gives you an idea. Now also, when we did not initialize it, the compiler did give us a warning. I'll just right-click here and compile. Notice the warning that the compiler is giving me down here. It's saying, warning, age is used uninitialized in this function. That's a clue. Don't ignore those warnings. The compiler is telling you, be careful, you're using something that you never initialized. Okay, so that gives you an idea of what's going on with uninitialized variables. All right, so let me erase this and let's write our program. So what we need here is we need to ask the user for the length of the room and the width of the room. We'll grab those two values from cin, then we'll multiply them together and we'll display the square footage of the room. Really, really simple program, but let's get started. So what we'll do is we'll say cout, and remember I don't have to use standard scope resolution operator here because I'm using namespace. So I'll say enter the width of the room, and we'll assume this is in feet. We'll put a semicolon at the end of that line to terminate it. Now we need to read something into a variable, right? So we need to do cin into something. Well, we need to declare that variable. Let's declare it right up here. We could call it width, and it's going to be in integers, let's say. Remember, we've got to say the type, followed by the name of the variable, followed by a semicolon. This is perfectly fine. Width is probably not a great name. Something like room width is better. It provides much more information to whoever's going to come later and modify this code. So now we've got the room width, and I'm going to enter the room width, and I'm going to read it into room width. Right, now we've got our variable. Now you'll notice a couple of things. One is we never initialized room width. In this case, it's probably okay because I'm going to read something into it before I use it, but best practice is let's initialize that. We'll set it to 0. Now we need another variable, right? We need the length of the room. So I'll just cut and paste this to save a little time here. And I'm going to say enter the length of the room. And we're going to read that into another variable called room length. And again, we'll initialize that to 0. In this case, 0 is fine. You could initialize it to anything that makes sense in your application. All right, so now we'll read that one into room length. I'll just change this variable name right here. So look at what's going on here. We've initialized two variables, room width and room length. They're both integers. Again, notice the syntax. The type name is integer followed by the name of the variable, and in this case, we're initializing it. I'm prompting the user to enter the width of the room, and I'm reading that integer into room width. Then I'm prompting the user to enter the length of the room, and I'm reading that integer into room length. All I have left to do now is just say cout, and I'll say the area of the room is, and we'll do the calculation here right in line. It's going to be room width times room length. And we may as well say square feet. That's it. We'll complete this with an end line. And I'll clean a little bit of this space up just to make it a little bit more readable. That's it. We're returning 0 at the end. Now let's build and run this. We get a clean compile and it says enter the width of the room. Let's say that the width is 10 feet. Enter the length of the room. Let's say it's 5 feet. Always remember, know what to expect. I expect a 50. Press enter. It says the area of the room is 50 square feet. So we get back what we expected. Always think about what you're going to get back before you do this. Otherwise, you may have errors that you didn't think about. We'll press any key to continue. That's it. That's a pretty straightforward solution. You can see how we use variables, how we can initialize variables, how you can read into variables. Now, a best practice would be, rather than declare these two variables up here, what we could do is we could declare them closer to where we're using them. So in this case, this is the first use of room width. So I could modify this by taking this line here, and I'll just cut it, and I'll paste it right in here. And I'll do the same with room length. I'll cut it from here, and I'll paste it right in here. And again, I'll just clean up the code a little bit, get rid of some of this extra white space. Now you can see what's happening. I'm prompting the user, I'm declaring that variable, I'm reading into it. I'm prompting the user for the length, I'm declaring the variable, I'm reading into it. So this is basically what we talked about in the previous slides. You can see this is a really simple example. Try it out, play around with it. There'll be a challenge exercise at the end of this section that's going to extend this a little bit. So that's the end of this video. This shows you how to initialize variables, use the variables. In the next video, we'll talk a little bit about scope and global variables. In our example programs, we've declared our variables within the curly braces of the main function. These variables are called local variables because their scope or visibility is limited to the statements in the main function that follow the declaration of the variable. This is generally what you want to do. However, sometimes you see variables declared outside of any function. These variables are called global variables, and they can be accessed from any part of your program. Unlike local variables, global variables are automatically initialized to 0. We'll talk more about scope and visibility as the course progresses. However, I wanted to introduce you to this concept here, since there's a lot of code out there aimed at beginning C++ programmers that uses global variables in their examples. Global variables have their place, but they also come with some potential problems. Since global variables can be accessed by any part of the program, this means they can potentially be changed from any part of the program. So if you've got a program that's thousands of lines of code, this can make finding errors and debugging more difficult. Let me show you an example of using global variables in case you see code like this out there as you study C++. I'm in the CodeLight IDE, and you can see that I've declared a variable called age. And age is declared right here, and it's within the scope of main. What that means is that this is a local variable. In other words, it's local to this function. So I can use age within this function. So for example, here I'm using age, and the compiler is going to say, okay, which age are we talking about? And it's going to find the age right here. So if I run this, it'll replace age with 18. This is the way we're going to program in this course. However, you may see code out there that looks a little bit different. Let me show you how that works. You may see code out there where this is not declared inside of main. Instead, it's declared outside of main. This makes age a global variable, which means that it can be accessed from anywhere in the program. So now what happens, when the compiler sees age here, first it looks locally to see if it has a declaration of age. In this case, it does not. Then it looks globally to see if age has been declared at the global level. It has. It finds it right here, and now it prints out 18. Okay, so that's an example of a global variable. The concept, again, is pretty straightforward, and it's possible to have both global variables and local variables. So I could do something like this. I could say int age is 16. And notice that now I have two variables named age. I've got one that's local and one that's global. When the compiler sees the use of age in the output statement, first it looks locally. It looks right here, it finds this age, and it's going to use 16 here. It will not use this one. So this one shadows the outer global variable. That's really all there is to global variables. Lots of times you'll see code, as I mentioned, where you won't see this here at all, and everything is global. They're okay for teaching purposes, but it's really not a good practice to start using global variables all over your code. In this video, we'll learn about some of the commonly used C++ primitive data types. These types are also sometimes called fundamental data types because they're implemented directly by the C++ language. The types we'll discuss in this video are the character types, the integer types, which include both signed and unsigned integers, the floating point types, and the Boolean type. It's important to keep in mind that unlike many other programming languages, the size and precision of C++'s primitive data types are largely dependent on the platform that you're working on and the compiler you're using. This means that as a C++ programmer, you need to be aware of your specific machine and understand how much storage is allocated for these types to effectively use them. The C++ include file climits contains information about the size and precision of the data types for your specific compiler. As you know, computers store information using a binary representation which consists of zeros and ones. And these fundamental type sizes are expressed in bits. The more bits allocated to a type, the more unique values that can be represented. Also, the more bits, the more storage that's necessary to represent that type in memory. In this table, you can see how many values can be represented in a given number of bits. The formula used to calculate these values is 2 raised to the number of bits power. So we can store 256 distinct values in 8 bits, 65,536 distinct values in 16 bits, over 4 billion distinct values in 32 bits, and over 18 billion distinct values in 32 bits. Now let's take a look at the specific primitive types one at a time. The C++ character data type is used to represent characters such as the letter A, X, and so forth. The character data type is often implemented as 8 bits, which means it can represent a maximum of 256 characters. This is plenty to represent the alphabets for many spoken languages. However, some spoken languages have thousands of characters, and in many cases, multiple symbols are combined to form single characters. In order to support these languages, C++ supports a wider character type that can be as large as necessary to represent these characters. Unicode is a common standard used to represent multiple character sets for any language. When we work with characters in this course, we'll use the char data type since it easily supports the Latin character set. C++ also supports the integer data types. Integers are used to represent whole numbers. Both signed and unsigned integers are supported. There are many variants of the integer data type. Let's take a look at some of them. The following tables show the C++ integer data types for both signed and unsigned integers. In addition to those shown in the table, it's possible to store both signed and unsigned integers in the character data type. Notice that some of the keywords in this table are bold and others are italicized. Also, typical sizes are included in the table. For example, if you want to declare a signed integer, you don't need to use the signed keyword, since by default integers are signed. Similarly, if you want an integer type that stores very large numbers, you can simply declare the type as long, and you'll get a signed long integer. If you want unsigned integers, that is, integers that are 0 or positive values only, then you're required to use the unsigned keyword. I know this may seem a little confusing with all the optional keywords, but it's not so bad if you just think that by default, all integers are signed. I know what you're thinking. Which ones of these do I use in my application? And the answer is, it depends. If you want an integer variable that stores ages, then you could use an unsigned int or even an int. If you want an integer to represent the number of kilometers between the planets, then you'd probably want to use an unsigned long. For most applications, using int is perfectly acceptable, but you do need to keep in mind the limitations, especially when you perform math on variables and store results in other variables, since the results may not fit into the variable you're saving to. This could cause an overflow. We'll look at a specific example of an overflow in live code at the end of this video. C++ also supports floating point types. These are used to represent non-integer numbers, such as real numbers like 1.2, 0.5, and pi. It's important to understand that computers have finite storage, and many real numbers have an infinite number of digits after the decimal point. Pi is a perfect example of this. In these cases, computers store an approximation of the real number. There's no way the computer can store numbers such as pi precisely. Floating point numbers are represented internally by the computer as signed numbers with a mantissa and an exponent. You may remember your scientific notation from school, 1.234 times 10 to the 7th power. That's the way they're stored internally. This isn't something you need to worry about since it's handled automatically internally, but it's important to know that these are approximations. There are 3 types of floating point numbers: float, double, and long double. Each has varying precision and size depending on the compiler. Note that long double can store very small and very large floating point numbers. The last primitive we'll learn about is the Boolean type. The Boolean data type is used to represent true and false values. In C++, 0 is false and any non-zero value is true. C++ also includes the true and false keywords that are often used with the Boolean type. As you can imagine, Boolean types are used whenever you need to know if something changes state. For example, game over, key pressed, is invincible. These are all good examples of using the Boolean data type, since their values can be either true or false. Great, now let's head over to CodeLight and see some of these primitive types in action. So now I'm in the CodeLight IDE, and I've created a project called Primitive Types that's in the Section 6 workspace. In this C++ file, I'm going to go over some examples of using the primitive types. We'll start with characters, we'll do integers and floating point numbers, and then at the end we'll do Booleans. And I'll also show you an example of an overflow so you can see the typical behavior you get with those. I've written the code ahead of time and I've commented out a lot of it, and what I'll do is I'll uncomment and run pieces of it at a time so you can see it build. So the first thing we want to do is take a look at this first example here. This is a good example of using the character data type. My middle initial is a J, so the variable name is called middle initial, and it's of character data type, so it can hold a single character. The way that C++ represents single characters is with single quotes around the J. Do not put double quotes there, that would make it a string and you'll get an error. So what I'm doing here is I'm simply initializing the middle initial variable to J and then displaying it right here in the output statement. So I'll build and run. And I'm just going to click here, remember, so it doesn't ask me my choice all the time, and I just want to build and execute. You can see here it says my middle initial is J, exactly what I expect. Okay, so now let me uncomment the integer types here. The way that you can comment and uncomment lines very easily is just select the lines you're interested in and just press Control/ or Command/ on a Mac, and that will toggle between a comment and non-comment. Okay, so in this case, I've created a variable called exam score, and I'm initializing it to 55. Now, exam score is an unsigned short int. Remember, we have to say unsigned if we want our variables to be unsigned. But I don't have to say int, I can simply say short. So this is the same as saying unsigned short exam score. Okay. So I'm initializing that to 55, and again, I'll build and run. And now you can see my middle initial is still J, and my exam score was 55. Okay. In this case, we've got another number, and I'll uncomment that out. The number of countries represented in my meeting were 65, and I'm initializing it. This is a simple integer. By default, it's going to be signed. And here it's going to say there were 65 countries represented in my meeting. So let me run that again. I'm pressing Control F5 on Windows just to use the shortcut. And you can see here there were 65 countries represented in my meeting. Now in this case, we've got a much larger number. Let me uncomment these two lines out. So now I've got people in Florida. That's my variable name. This is the state I live in, and there are 20,610,000 people living in Florida. The last I just checked on Google. So I'm defining this as a long. I'm hoping that that fits in the long. It's a pretty big number. I'm pretty sure it does. Let's try that. So I'll press Control F5 again. We'll run it, and you can see there are about 20,610,000 people in Florida. Now in this case, how about number of people on Earth? I'll uncomment those two lines, and you can see my variable name is people on Earth, and there are about 7,600,000,000 people on Earth. Now something that's interesting is as these numbers get bigger and bigger and bigger, they're hard to read, and it's really easy to forget zeros and so forth. So the C++ 14 standard allows you to use those little tick marks right there. You can put them anywhere you want. It really doesn't care. Just to make it easier for you to read, it strips them out and just creates the number. If this doesn't compile on your end, most likely you're not using the C++ 14 compiler, you're using the C++ 11 compiler. You could set it to C++ 14, or you could just get rid of these little tick marks to make it compile. So when I run this, you'll see something interesting happen. I'm pressing Control F5 again. Notice I'm getting an error. The error says error narrowing conversion. It's trying to fit that number into a long, and it doesn't fit. This is one of the benefits that I mentioned about using the list initialization right here with the curly braces. Notice what happens if I did, but actually, you know what? Let me just run this first as a long, which is really what I want, because otherwise it's not going to fit. So now I've got my long, and I'm going to build and run this. And you can see there are about 7 points. You can see the number is correct. Okay. But if I did a regular initialization, like a C-style initialization with an equal sign here, or an assignment statement, something like that, and we'll go back to long, because we know it's not going to fit in a long, and I'll build and run again. Look what prints out. There are about negative 98999 people on Earth. That's an example of an overflow. But you also notice that we didn't get an error. That's one of the benefits of using the list initialization. If I use list initialization, it will catch those problems for me at compile time, which is really, really nice. So again, I'll compile here. I'll Control F5. Boom, there's the error. I know I've got a problem. I can fix it. So I'll make this a long. Okay, so hopefully that makes sense. Always use that list initialization syntax. It's so much better. In this case, I want the distance to Alpha Centauri. That's pretty far. This is, I believe, in kilometers. Yep, it's in kilometers, because that's what my output statement says. I'll uncomment these two lines. And let's run this. And you can see that the distance to Alpha Centauri is, and that's my number. That's correct. Okay, so that's a good example of an overflow. I'll show you another example of an overflow at the end of this source code that may not be as obvious as this. Okay, so here's a couple of examples using floating point types. Remember, these are real numbers. These are numbers with decimal points. So in this case, my car payment is $401.23. I can uncomment this out. Obviously, if I try to store 401.23 into an integer, I've got a problem because the integer would only hold the whole number. So the 0.23 would get truncated off, and I could have a problem. Okay. So in this case, let's run this. And now you can see that my car payment here is $401.23. Okay, if I want to store a larger number, I could use a double. In this case, I'm just storing pi. In this case, I'm hard coding pi to be 3.14159. It could be obviously much, much longer. And in this case, it's a double. And you can see that there's pi 3.14159. I can also store very large and very small numbers using long doubles. So in this case, I'm storing 2.7 times 10 to the 120th power. That's a very large number, and I'm going to store that into this large amount variable, and then I'm going to display it. So let's build and run. And you can see 2.7 times 10 to the 120th power is a very big number. You can see it's actually storing that correctly. The last one we'll look at is the Boolean type. The Boolean type is a true-false value. So in this case, I'll comment that out. You can see I've got a variable called game over. Let me use the correct underscore style here. I've got a variable called game over. And in this case, you could see that I've been working on a project that's using camel case. Muscle memory kicks in. So in this case, I've got a variable called game over, and I'm initializing it to false. And then I'm saying the value of game over is, and you might expect that this would print out false here, but it doesn't print out false. What it does is it prints out 0, because as far as C++ is concerned, 0 is false. If it was true, it would print out a 1. Now here's an example of an overflow that's not so obvious, and I'll comment that out. Here I have a variable called value1, and I've got another variable called value2. They're both short integers, and I'm assigning 30,000 to this one and 1,000 to this one. Those numbers will fit in those variables. But then I'm going to create another variable called sum, and I've got value1 times value2. Now I know that the product of those, I guess I should have called it product, huh? Let me call it product just to be a little bit more correct here. There we go. So I know that the product of those two numbers does not fit in a short. So let's compile this. And you can see that the sum of 30,000 and 1,000 is some negative number. Obviously, that's an overflow error. Be very careful with these things. Make sure that, sure, those two pieces each will individually fit in the shorts, but the product certainly can't. Okay. But notice the compiler is helping me here. The compiler is saying, warning, you've got potentially a narrowing conversion here. So don't ignore those warnings, as the compilers do a pretty good job about predicting problems that can happen. Okay, so that concludes this video. You can see some simple examples of creating variables, initializing variables, using some of C++'s primitive types. In this video, we'll learn about C++'s size of operator and about the C-limits and C-float include files. C++ has an operator called sizeof that returns the number of bytes used to represent any type. Sizeof can also be used to determine the size of compound types like arrays, structures, and objects. We'll learn about compound types in a future section. In order to determine the size of a specific type, we provide the name of the type inside the parentheses. For example, size of int, size of double. This will tell us the size of that type in bytes on the specific machine and compiler that you're running the program on. You can also determine the size of variables using their names. In this case, you can use the same syntax, or you can omit the parentheses since they're optional for variables. The sizeof operator gets its information from two C++ include files, C-limits and C-float. C-limits provides information about integral types, and C-float about floating point types. These include files also provide a bunch of handy defined constants that we can use to determine the precision of our primitive types. For example, int max tells us the maximum value we can store in an int on this specific machine. There are many others, and you can see some in the examples in this slide. Let's head over to the CodeLight IDE, and we'll see what some of these values are on my machine. I'm in the CodeLight IDE, and I've written some code that uses the sizeof operator. Let me walk you through it. First thing we'll see is that we're including IOStream, and we're also including C-limits. Everything I'm using here will use C-limits. You can get the same information in C-float, and I'll leave that as an exercise for you if you like. First thing we'll do is we'll output sizeof information for types. So in this case, I'm going to output char, followed by size of char in bytes. size of int, size of unsigned int, short, long, and long, long. Now, when I run this, I'll get information about how big or how much storage is necessary to represent a character, an integer, and so forth on my specific machine using this specific compiler. Okay, now the rest of the code is commented out, and again, I'll uncomment that as we go through. So what I'll do is, and I've created a project here called size of operator project, and you can run this code on your machine and see what your values look like. So I'll build and run, and you can see the size of information that's come up. A character is 1 byte, an integer is 4 bytes, an unsigned integer is also 4 bytes. That makes sense because the only difference between an int and an unsigned int is that signed bit and how much precision you can store in it. A short integer is 2 bytes, a long integer is 4 bytes, a long integer is 8 bytes, and there you go. Now, I'm running a 32-bit compiler on a 64-bit operating system. If you're running a 64-bit compiler, these numbers will likely be different. All right, so that takes care of the basic size of for the integral types. Let's look at some of the floating point types. So in this case, you can see that I want the size of a float, a size of a double, and a size of the long double. Okay, so what we can do is we can build and run, and you can see now that a float on this particular machine, again, is 4 bytes. A double is 8 bytes, and a long double is 12 bytes. So that's the amount of storage that it takes to represent these specific types on this machine. Okay, so now the CLimits file contains some pretty nice defined constants. And let's use some of them to see what it's like. In this case, I want minimum value. So I want to know what's the minimum value that I can store in a character. What's the minimum value that I can store in an integer, in a short integer, in a long integer, and in a long integer. And you can see the defines are right here, and those will default to some integers. So let's run this now. Again, I'll build and run. And you can see that the minimum value I can store in a character is -128. That makes sense because a character is 1 byte big. In an integer, you can see the number there. In a short, -32768, the long, and the long. Your numbers may look different on your machine depending on a lot of factors. All right, now we can do the maximum values. And it's exactly the same except we're doing char max, int max instead of char min and int min. I'll run this again and I'll press Control F5 to run. And now our maximum values are for characters 127, for short 32767, and for longs you can see that's a pretty big number. All right, so that's the use of CLimits and size of with types. We can also use size of with variable names. And I'll show you an example here where what we have here is, here we've got an integer called age, and we're assigning 21 to it. We're not going to use the 21 at all. All we're interested in is the size of that variable. So rather than size of int, here we're saying size of age. This is one syntactic variant. We can also just say size of age without the parentheses. So I'm doing that for an integer called age, and I'm doing the same for a double called wage. So obviously we would expect the double to be much bigger. But again, what I'm doing in here is I'm using the variable name instead of the type here as well. All right, so let's run this one more time. And what we've got now at the bottom here is that the size of using variable names. So age is 4 bytes. And if you recall here, we know that age is an integer, right? And integer up top is 4 bytes, if you recall that statement at the top. So age is 4 bytes. The other syntax variant gives you exactly the same result. And wage is a double, which is 8 bytes. And you can see our doubles here is 8 bytes. You may be wondering, when in the world would I ever use this stuff? Well, it's important, A, to understand what the size and precision of your types are on your system. Later on, when we deal with arrays and other data structures, sometimes it's nice to be able to understand how big something is, how big each section of it is. This is one of the big differences between C++ and other languages like Java and Python. With those languages, you're really far removed from the machine, so you're programming at a much higher level. C++, we're at a lower level, so we've got to deal with this kind of thing. In this video, we'll learn what constants are in C++. Constants are very much like C++ variables. They have names, the rules for naming is the same, they occupy storage, and they're usually typed. This means that when you declare a constant, you usually declare their type just like you do with a variable. There is one type of constant that is not typed, and I'll talk about that at the end of the video. The big difference between variables and constants is that unlike variables, the value of C++ constants cannot change once they're declared. For example, if I declare age to be a constant integer and assign 21 to it, then the value of age will always remain 21, and I won't be able to change it. If I try to change it, I'll get a compiler error. Why would you need constants in a program? Let's consider a simple application that uses the number of months in a year throughout the code. We could certainly use the number 12 everywhere we need it. However, 12 could mean a lot of things. And if the program is of significant size, it might not be clear to other programmers that 12 means the number of months in a year. So we could create a variable and call it months in a year and assign 12 to it. And now use that name in our code whenever we need to use 12 in that context. That's a much better solution than hard coding 12. But that's a variable, which means that it can be changed, even accidentally. A better solution is to declare months in a year to be a constant integer and assign 12 to it. Now we can use a meaningful name in our code that means 12, and we can't change it even by accident. C++ gives us several ways to create constants. We can use literals, declared constants, constant expressions, enumerated constants, and finally we can use defined constants. We'll learn about constant expressions and enumerated constants later in this course. Let's see what literal constants are first. Literals are the most obvious kind of constant. We can use literals throughout our code, and we often do. They're used to express specific values. We've already seen examples of literals. In this slide, you can see that 12, 1.56, Frank, and the character J are examples of literal constants. For example, the floating point literal constant 1.56 always expresses the value 1.56. Literal constants also have types based on a naming convention. You can be explicit with the types of literal constants. For example, for integer literal constants, you can add certain suffixes to the integer literal to specify a different type. For example, the letters U and L specify unsigned and long respectively. These can be either lowercase or uppercase. This slide shows just a few of the combinations. For floating point numbers, you can use the L and F suffixes as shown in this slide. We can also have character literal constants in C++. We haven't used these yet, but they're commonly used within string literals. They consist of the backslash character followed by another character, and they're called escape codes. You can see some examples in this slide. The cout statement will display hello, then tab over and display there. Then it will go to the beginning of the next line and display my friend, and then it will go to the beginning of the next line again. It's very common to see escape codes embedded in string literals and output statements. By far, the most common way of declaring constants in C++ is to use declared constants using the const keyword. The syntax is exactly like that of a variable declaration, with the const keyword at the beginning. You must initialize the declared constant, or the compiler will give you an uninitialized const error message. What happens if you try to change the value of a constant? You guessed it, you can't. The compiler will give you an error letting you know that the constant is read-only and you can't change it. The last way of declaring constants in C++ is by using the preprocessor directive #define. Let's take a look at that. Defined constants were very commonly used in older C and C++ code. These constants are defined using the #define preprocessor directive. I'm showing you defined constants because you may run into them since there is so much C++ legacy code out there. Here you're telling the preprocessor that wherever it sees the word pi, replace it with 3.1415926. Think of this as a blind find replace, as you might do in a word processor. The preprocessor will gladly substitute one for the other. Since the preprocessor doesn't know C++, it can't type check, and this could lead to difficult to find errors. So please don't use defined constants in modern C++ code. In the next video, we'll head over to the CodeLight IDE and see how we can declare and use constants in C++. First, we'll write a program using literal constants, then we'll refactor the code to use declared constants. In this video, we'll apply some of the concepts that we've learned in this section to solve a problem. What we'll do first is we'll solve the problem using literal constants, and then what we'll do is we'll refactor it to use declared constants. And along the way, you'll see how much better it is to use declared constants. Okay, so here's the problem we're going to solve. Frank has a carpet cleaning service that charges $30 per room, and there's a sales tax rate of 6%. All the estimates are valid for 30 days. So our program is really simple. We're going to prompt the user for the number of rooms they would like cleaned, and we're going to provide an estimate. The estimate will look something like this. You can see here starting at line 13. Estimate for carpet cleaning service, number of rooms, 2. That's the number that the user entered. Price per room, $30. Cost, $60. Obviously, that would be $30 per room times 2 rooms. The tax, which would be 6% based on the $60, which would be $3.60. Then the total estimate would be $63.60, and then you print out this estimate is valid for 30 days. Now I'm using dollars, you could use euros, you could use any currency you like. Also, I know that the formatting isn't right. Obviously, $3.60 would be 3.60. Don't worry about that right now. Let's worry about solving this problem and using literal constants and using declared constants. We'll worry about output formatting in a different section, and we'll go over a bunch of different ways to do formatting, including currency formatting based on your locale. All right, so let's think about how we're going to solve this problem. Programmers often use something called pseudocode. Pseudocode is like an English-like or your own natural spoken language-like representation of the algorithm or the steps necessary to solve the problem. In this example, I wrote down some pseudocode. And pseudocode, don't let anybody tell you that there's a right way and a wrong way to do pseudocode. There really isn't. It's not a programming language. This is something that organizes your thoughts and allows you to solve the problem. Remember, if you can't solve the problem in pseudocode, there's no way you're going to solve it in C or in Java or in any other programming language. So in this case, this is my pseudocode. These are the steps that I want to take to solve this problem. The first thing I want to do, and you can see here on line 23, is prompt the user to enter the number of rooms. Great. I want to display the number of rooms to the user, display the price per room. Then I want to display the cost, which is the number of rooms times the price per room. I want to display the tax, which is the number of rooms times the price per room times the tax rate. Then I want to display the total estimate. The total estimate, of course, is the cost plus the tax. And then I want to display at the end, this estimate is valid for 30 days. So what we want to do is we want to mimic this sample output right here. Okay, so let's get started. What we'll do first is we'll do this using literal constants, and then we'll refactor it using declared constants. So the first thing I'm saying is, hello, welcome to Frank's carpet cleaning service. That's my little introduction. Now I need to ask the user, again, look at the pseudocode, ask the user how many rooms they'd like to be cleaned. Okay, so let's do that. We'll say cout, and we'll say how many rooms would you like cleaned? And I'm going to type this along, and if I make typos and errors, that's fine. I'll fix them along the way, and you'll probably make the same kinds of errors, so you'll see how to fix them. Semicolon at the end, and there's a typo right here. So how many rooms would you like cleaned? Now, let's run this. And what I'm doing is I'm pressing Control F5, which is build and run. And you can see here, hello, welcome to Frank's carpet cleaning service. How many rooms would you like cleaned? Perfect. Now I'd like to put a space between the first line and the second line of output. Now there's a couple of ways I can do that. I can come down here and I could just add another end line, and that'll print 2 new lines at the end, which would be fine. I could also just say cout end line here, which prints out a line. Let's run that and I'll show you what that looks like. Now you can see that there's a line between the first line and the second line. And I can also use a character literal constant right here. And in front of the how, I can put a /n, a \n. That's a new line. Now I can get rid of this, and it has the same effect. So what's going to happen here is it's going to print a new line before it prints the how. So if I run this now, you can see I get the same effect. So this is an example of embedding those escape codes, as I mentioned in the PowerPoint slides, into string literals. So now we're here. Next step is to read in the number of rooms from the user. So obviously we need to use the extraction operator with the cin object, but we need to store that somewhere. So let's create an integer, We'll create a variable here, and we'll call it number of rooms. Best practice is to initialize it, so I'm going to initialize it to 0, and cin, and let's get the number of rooms from cin. Okay, so again, let's see where we're at. We've outputted our prompt, and the user has entered the number of rooms. Now we've got all the information that we need to do our calculations. We know that it's $30 per room, and we know that it's a 6% tax rate. That's all I need. So let's create some output statements, and I'm going to close this down here just to create a little bit more room. All right, so let's go here, and we're going to say cout, and let's put a /n here too, because I'd like a space right here. So I'm going to say estimate for carpet cleaning service. We'll create a new line here. Now we want to display the number of rooms to the user. I'll say number of rooms, and I'll put a $sign in here. I'm not too worried about the formatting. I'm just using dollars, so I might as well put the $sign here. And I want to display the number of rooms. Where do I get that? Well, I get that right from here. That variable right there, the user just entered a number, and I stored it in there. So that's going to contain whatever they entered. So there's number of rooms, and then end line. All right, let's run this. Control F5, and I've got an error that says I forgot to put an L at the end of the end line. There we go. So let's run this again. How many rooms would you like cleaned? Let's say I want 2 rooms cleaned. Estimate for carpet cleaning services, number of rooms 2. I don't want $1 there. I want $1 for prices. So that I'll fix that error. 2 rooms. Perfect. Okay, so now let's start doing some of the calculations. But first, we need to print out the price per room. And that's a given. That was given to us as $30. So we'll say price per room. Here we'll put a $sign. And we'll say 30. We'll use a literal right in there. And we'll say end line. All right, so that's it. Then we'll say, what's the cost? Well, we'll have to do a calculation. So we'll say cout would be cost. And again, I'll put a $sign in here. And what's the cost going to be? Well, the cost is going to be 30 times the number of rooms, right? $30 per room times the number of rooms. And we'll put a new line at the end. Let's test this out as we go. So let's run it. I want 2 rooms cleaned, so I expect the cost at this point to be $60. So 2 rooms, $30 per room, costs $60. So we're good. All right, so let's continue. And we'll say cout, what's my tax? Or my sales tax is, again, I'll use $. And my sales tax is going to be the same calculation, right? 30 times the number of rooms. And I've got an extra quote character right here. Let me get rid of it. 30 times the number of rooms times 0.06, which is the tax rate. End line. I'll save this. Let's run one more time. 2 rooms cleaned, $30. It's $60. 6% of 60 is $3.60. Okay, so we're good. Now we're going to calculate the total estimate, which is going to be the cost plus the tax. But first, I just want to print out a nice little line that separates everything together. That's long enough. And I'll put an end line at the end. All right, so now let's say what the total estimate is, and then we just need to say the estimate is valid for 30 days, and we're done. So cout, we'll say total estimate, and again in dollars is going to be, okay, we need to do the calculation again. So we're going to say 30 times the number of rooms, which gives us the cost, right? And I'm going to put some parens around that because I need to add to that plus 30 times the number of rooms times 0.06, which is my sales tax. So that's my cost plus my sales tax and a new line at the end. Last thing is, let's say cout this estimate is valid for however many days, and we said 30. And I'll put a space in front of the D just so we have a little room. Another line here, and I think we're good. Let me clean this up a little bit down here so it all fits a little better. All right, so let's run it, and then we'll go over it real quick. I'm going to save it and run it with Control F5. How many rooms would you like cleaned? 2 rooms. Number of rooms is 2. The price per room is 30. The cost is 60. The tax is 360. So you would expect the total estimate to be 6360, which it is. This estimate is valid for 30 days. Cool. Let's try it again. Let's run it again with 1 room this time. 1 room is $30. The cost is $30. The tax is $1.80. Total estimate $31.80. So it looks good. Don't forget to test with 0. So 0 rooms cleaned, 0 cost, 0 tax, 0 estimate. Great. Don't worry about testing with illegal values. We'll learn how to deal with illegal values later. So for example, expect it to users going to type 0 or something positive in the number of rooms. They're not going to type in -1 or Joe or Frank or anything like that. As I said, we'll deal with exceptions as the course progresses. So that's it. That's the program. It works. It's pretty easy to understand. It follows our pseudocode, but there's a couple of issues here. First, suppose that I want to increase my cost per room or my price per room to $32.50. What do I do? Well, I could do a search and replace, right? Let's do that. I'll do a search, find and replace. And I want to look for 30, and I want to replace it with 32.50, and I want to do it everywhere. Replace all. Done. I'll close this up, and let's run it. So I want to do 2 rooms. 2 times 32.50 is 65. That's correct. The tax is $3.90. That's correct. The total estimate is correct. Looks good, right? Except for one little thing. This estimate is valid for 32.5 days. You can see that the 30 was replaced with 32.5. I didn't want to do that. So I need to go back to my code, and let's change that to 30. And now we're okay. This is easy to fix in this example because it's really small. But if you've got thousands of lines of code and you're doing search and replaces like this, it's real possible that that 30 is going to be in different places and it doesn't represent price per room. It represents something else. And you just really messed up your program. You made a lot of changes you didn't intend to change. So hopefully you'll see what I mean. I'm going to undo this 30. And I hope I'm back to where I was. Yep, I'm back to where I was with 30. What I want to do here is I want to use declared constants rather than these literal constants. So let's do that. First, let's just create the variable, and then we'll make it a constant. So we need something for the price per room. So let's create that. Let's say int price per room, and we can initialize it to 30. And then the idea being, instead of using 30 here, we'll use that name price per room. Okay. That's okay, but why an integer? That's really doesn't make too much sense, right? It makes sense with 30, but if I change the price per room to 32.50 or some real number like that, a floating point number, this won't work very well. So this really should be a double, and I'm going to change that right there. That gives us a floating point number, and the last thing I want to do is I want to make it const. I don't want that to change in my program. I'll always want it to be 30 while this program's running. Okay, now if I try to change that right here, I'll just show you real quick. Price per room, let's say I want to change that to 100. And I'll just compile over here. I'll get a compiler error that says error, assignment of read-only variable price per room. You just told the compiler that price per room is constant, and here you tried to change it. The compiler is saying, no way, you just told me that this should not be allowed. Okay, so that's one of the benefits of constants, as I mentioned in the lecture. So let me get rid of that. And so that's one of the constants we need. We also need another constant. I'll put a 30.0 in here to be more accurate because it is a real number. I need another one for the sales tax. So I could say const, again, double. And I can say sales tax or sales rate or whatever you want to call it. And in this case, it's 0.06. And then finally, let's create another one for the estimate expiry, which is the 30 days. Const, this case could be an integer, and we'll just say estimate expiry. And we'll initialize that to 30. And this will be a good place for a comment, days. Okay, so now we've got those three constants. What we can do now is let's go through our code and we'll replace that 30, for example, with price per room, that 006 with sales tax, and so forth. This is called refactoring your code. Refactoring means changing your code to make it better without changing behavior. That's real important. Refactoring does not change the behavior of your code. It just makes your code better, more modifiable, easier to read, and so forth. So let's do that. I'm going to use price per room here. I'm just going to copy it, and I'll paste it in here. I'll paste it in here. I'll paste it in here, in here, in here, and not in here because that's my expiry. I'll take sales tax. I'll copy that, and I'll paste it here, as well as over here. And then finally, we'll do the estimate expiry right here. All right, so now let's run this again. And the behavior should not change. I want 2 rooms cleaned. 2 rooms at $30 is $60, $360 sales tax, $63.60 is the total estimate, and it's valid for 30 days. Perfect. As you can see, this code is much more readable now. You can actually see what's going on. And more importantly, if I want to change the price per room to $32.50, I only have to do it in one place right up here. So I can make this $32.50, save it, build and run again. 2 rooms, $32.50, which is $65 now is the cost, $390 tax, $68.90, and it's still valid for 30 days. So you can see the benefits of using declared constants. You can just make changes in one place. You're guaranteed that they're not going to change even if you made a mistake and it was an accident. And it makes your code so much more readable and modifiable. Now, although this code is much better now after refactoring, it still has a few problems. And those problems we're going to address as the course progresses. You hopefully have seen that right about here, we're doing a calculation. And then right here, we're doing the same calculation again. And here, we're doing the same calculation again. And here, we're doing it again. Okay, so that's 4 places that we're doing the same calculation. That's 4 places we could mess up. We really don't want to do that. We want to do that calculation exactly in one place. And what we'll do is when we learn about assignment statements and a little bit more about mathematical expressions, we'll do that there. And then a little bit later in the course, we'll use functions to do that in exactly one place. So if you notice that this isn't quite right, you see a lot of duplication of code, you're absolutely right. And we're going to handle that as we go. All right, so let's get ready for the challenge. This is a pretty simple challenge that's based on one of the problems that we solved in this section. If you recall, we had a problem for Frank's carpet cleaning service where Frank charged so much per room. Well, this is a little bit different. In this case, Frank has 2 charges, one for small rooms and one for large rooms. So as you can see here, he charges $25 for small rooms and $35 for large rooms. The sales tax rate is still 6%, and estimates are still valid for 30 days. So what you need to do here is prompt the user both for how many small rooms they want cleaned and how many large rooms they want cleaned, and then provide an estimate that looks something like this. Number of small rooms, for example, 3, number of large rooms, 1, price per small room, $25, price per large room, $35, calculate the cost, calculate the tax, and then come up with the total estimate and tell them that the estimate is valid for 30 days. Okay, so hopefully that makes a lot of sense. And here's a sample run that you can see. So here, hello, welcome to Frank's Carpet Cleaning Service. How many small rooms would you like cleaned? Well, let's say I want 3 small rooms cleaned and 1 large room cleaned. And you can see here the estimate is number of small rooms 3, number of large rooms 1. That's what I just typed in. The price per small rooms is $25. The price per large room is $35. And the cost is $110. Now, if you do the math, you can see that 3 times 25 is 75 plus 35 is 110. 6% of that is $6.60. If you add it all together, you get $116.60. And then you display this estimate is valid for 30 days. All right, so give it a shot. Take your time. I'm sure you'll do it just fine. If you want to see the solution, in the next video, I'll present my solution to this problem. Welcome back. I hope you had fun trying to solve the problem. I'm sure you did great. As you noticed in the workspace, I created the challenge, which just created an empty shell for the problem. And I've also got the challenge solution, which has my solution to the problem. Okay, so let's start looking at the code here. We know what we had to solve. So let's look at some of these really simple statements first. And I'll mark this up just so it's easier for you to follow. So in this case, I'm simply outputting welcome. Then I've defined a variable here, which is going to hold small rooms, and I've initialized to 0. That's the best practice. I'm prompting the user, and I'm asking them to put in the number of small rooms they want cleaned. I'm doing exactly the same thing here, except we're doing large rooms. And now we've got to define two declared constants, right? We're going to declare one is the price for a small room, and one is the price for a large room, 25 and 35 respectively. We've got our sales tax declared constant here, and we've got our estimate expiry constant. So far, so good. It's exactly the same as we did before. The only thing is I'm adding the large rooms. Okay, so let me clear this, and I'll scroll up just a little bit, and let's take a look at some of the calculations. Here are some of the output statements, and you can see here I'm outputting the number of small rooms, which is just whatever the user typed in, and the number of large rooms, which is whatever they typed in. The price per small room and the price per large room right here, those are our declared constants, which I'm outputting. And now the cost. The calculation is really simple. It's the cost of the small rooms plus the cost of the large rooms. And we calculate each one by price per small room times the number of small rooms plus, and there's my plus sign. Remember, you can split these across lines so you can line up the insertion operators like that. It makes them nice and easy to read. So in this case, I'm just calculating the cost for the small rooms, and I'm adding the cost of the large rooms to it. Same thing with tax. I'm calculating the cost again, and I'm multiplying the whole thing by sales tax. Notice that I've got those parentheses here because what I want to do is I want to calculate the whole cost and then multiply that by the sales tax. Otherwise, I won't get the correct answer. Got to make sure the whole thing is here. So this becomes all the small costs plus all the large costs. Okay, then finally the total estimate just takes the cost and adds the sales tax to it. That's it. The estimate is valid for 30 days, and there's my program. So you can see that my formatting is probably going to be a little bit different from your formatting, and mine might be a little bit more readable. You may not have split things across lines like I did. It's real good practice to split these across lines. That way you can really see what's going on, and it's much, much easier to follow. Okay, well, I hope you enjoyed the challenge, and I hope you did well. Remember, there's a lot of duplicated code here that we're going to clean up as the course progresses. And this program, we'll actually modify this program a little bit later on when we use functions. Okay, so that's it for the challenge.